Okay, the last thing we need to talk about in this set of notes is the tangent and normal, and then something called the binormal vectors. This is going to be a little bit challenging because I can't actually like show you using the right hand rule, so this might be a good thing for us to talk about this week, although I do have a couple of little animations in the notes for you today. So one thing that we know so far is that differentiating a vector valued function gives us the tangent vector, which one thing that's like a little bit counterintuitive is that the tangent vector is not always orthogonal to the original function. So one thing that I tried to do when I was drawing the picture of the tangent vector a couple pages ago was make it really clear that you can have something like a tangent vector that is not orthogonal. So in other words, this is not a right angle to your original vector. So one of the things that we really appreciate in multivariable calculus is orthogonal vectors. So this entire section is about 3 specific orthogonal vectors, and we even go one step further to make them a little bit more convenient, which is normalize them and make them all unit vectors. So the whole reason that we have this like dividing by the magnitude on the bottom is that this, what we call is, normalizes your vector, which just means makes it a unit vector. When you divide by its magnitude, it just makes it a unit vector. It makes it length 1. So you'll notice that both of these first 2 definitions are normalized. So these are both unit vectors. So this tangent vector, what we really define to be the tangent vector, is just the derivative of your original function, but then normalized. So this is really the unit tangent vector. It's the tangent vector, but it's length 1. And then we define the normal vector. You've seen this in single variable calculus as well. The normal vector to be the one that is orthogonal to the tangent vector. So this is the unit normal, which is the derivative of the tangent vector normalized. Now, one thing that's like a little bit weird about talking about the tangent vector and then the normal vector is in 2 dimensions. I'll try to draw this over here. In 2 dimensions, it's very clear sort of which direction would be normal. So like if you have your tangent vector here, then you have your normal vector going like this, and you know that they're at a 90-degree angle from each other. But once you're talking about a vector in 3 dimensions, you kind of have like all these different possibilities for right angles, and it's not exactly clear like which one would be called the normal vector. So that sort of brings up this definition of binormal that we'll get to in a second. But just in case you're wondering like what does normal mean in 3 dimensions, we will get to that with the binormal vector. So first of all, let's just use the definitions to find the tangent, the unit tangent vector, and the unit normal vector for this sort of general circular helix. Now I'm not fixing these coefficients in the front. They can be anything. So A is just a constant, C is a constant, but let's just do this first example and actually find some of these tangent and normal vectors for those 2, for this sort of friendly helix function. So in order to find the tangent vector, we just need to differentiate our original function, our original vector valued function. So our original vector would just be, here's the first component, second component, third component. I'm just going to differentiate component-wise. So A is a constant, so that just stays there. So I'm going to have negative A sine of t as my first component, A cosine of t as my second component, and then just C as my third component, because when I When I differentiate c times t, only the constant sticks around. And then I need to just normalize this vector. I mean, this right now is a tangent vector. It's just not a unit tangent vector. So I'm going to normalize it. And the way that I normalize it is by dividing by its length. I just divide by its length, and that's going to give me this unit tangent vector. So the length of this thing, which is actually going to come out to be sort of nice, is the square root. I'm going to square each component. So a squared sine squared of t plus a squared cosine squared of t. And something should stand out to you there because I've got a sine squared plus a cosine squared. So those are going to cancel out to 1. And then I have third component here, c squared. So really, this entire thing cancels out, and the bottom, this whole square root just gives me, I'm just going to write it right here, square root of a squared plus c squared. So my entire tangent vector, my unit tangent vector, would just be negative a times sine of t over the square root of a squared plus c squared. There's first component. A cosine of t over the same thing. There's my second component. Sorry, this is so messy. And then my third component is just c over the square root of a squared plus c squared. And there's my third component. So this is my unit tangent vector. Now, it was much nicer back before we normalized it and we just differentiated, but a lot of times we like to mess with the lengths of these vectors, and we like to, you know, do things like cross product and finding dot products of them. It's just a lot nicer for us when the magnitude of all the vectors that we're dealing with is 1. So what you'll notice a lot of times is that we'll start with a really nice vector and then we'll normalize it and it becomes ugly, but it actually is a lot nicer geometrically for us to work with. So there's our tangent vector. Now, I basically just do the exact same process again to find the unit normal vector. So using that, I just need to find the derivative of the tangent. So let me write this down. Okay, so our unit normal vector is going to be, I'm going to start with the derivative of this guy, which is going to be pretty hideous, except that I guess the denominators of these are all just constants. So I was thinking it was going to be pretty terrible, but it's actually not. So I just need to differentiate the top of the first component, which is going to give me negative a cosine of t, negative a cosine of t, and then I'll leave the denominator alone because that's just all a constant, so a squared plus c squared. And then differentiate the top component here, so that's going to be negative a sine of t, and leave the bottom alone because it's a constant, plus c squared. And then the nice thing is this entire third component is just a constant, so that goes away. Now, that's only this part of our formula. I have not divided by the magnitude of this entire thing. So I am going to, where am I going to do this? Let's see. I'm going to erase what I have over here because I need a lot more room. Now, I'm going to cheat a little bit here and just move that up. The magnitude of this vector, because that's what I need to divide by, is just going to be this squared plus this squared all under a square root, which I think is actually going to clean up pretty nicely. So here's a big square root, and then I'm going to have a squared cosine squared of t on the top here, and then when I square the bottom, it just turns into a squared plus c squared. I'm going to do the same thing here, square this entire component. So a squared sine squared of t, sine squared of t, over, and square the bottom again. I don't need to do anything with the third component because it's just going to go away. I'm sorry, because it's already 0. Again, I have this cosine squared plus sine squared, so the entire top just turns into just a squared, and this whole magnitude becomes the square root of a squared over a squared plus c squared, and I'm just going to simplify it by taking the square root of the top, and I'm going to say a over the square root of a squared plus c squared. So there's the magnitude. That's what's on the bottom of this whole thing. I still have the rest of this vector on the top. So when I simplify this, and again, this is such bad form, but I'm going to erase what I just did. And instead of dividing by this fraction, I'm going to multiply by its reciprocal. So I'm going to put this square root, because this is going to clean up really nicely, here, and then a on the bottom, and a whole bunch of this is going to cancel. So both of these square roots are going to cancel with that one. The a's are going to cancel out, and I think my final answer, when I'm all done with this, is just going to be negative cosine and negative sine and 0, and that's it. So there's my unit normal. I erased my unit tangent, but those two things were orthogonal. And now I guess the interesting question is, we are dealing with 3 dimensions, so it seems like we could have a third sort of like primary dimension component in our picture, and that's what brings us to the binormal vector. So on this picture, this is a vector valued function, this little spirally guy. The easiest one for you to recognize is going to be the tangent vector. You can just tell it's tangent to this function. We must be traveling along this way because the tangent vector came off in this right direction. And the normal vector is the one that we just found in our example, so that's going to be heading up this way. Now, I know that this is sort of at an angle, but I want you to try to use the right hand rule here. Like, hold your pointer finger in the same direction as the tangent vector, and then you'll have to flip your palm upward and hold your middle finger so that it's in the direction of this normal vector. So you'll have your right hand pointing, sort of like your pointer finger pointing to the right, your middle finger pointing up, and that creates, it sort of forces your thumb to be pointing back sort of toward you. And that third component, that third direction, is the direction of this binormal vector. So the entire process here creates 3 vectors that are not only orthogonal to each other, actually the most important thing is that these vectors basically give you like a mini XYZ axis. They give you like this mini 3-dimensional space with these directional components. So tangent, normal, binormal. The binormal would sort of be analogous to the z-axis, whereas you have this tangent being the x, normal being the y. It just makes sense for us to define a z-axis also, since we're dealing in 3 dimensions. So tangent, normal, binormal. And then I guess we would be wondering how we could find the binormal vector, but remember, the whole use of the cross product that we talked about last time is to define this third vector that is orthogonal to the other 2. And orthogonal, not just orthogonal, orthogonal in exactly the proper configuration using the right hand rule. So once you have the tangent vector, once you have the normal vector, or the unit tangent and the unit normal, you cross those together. So remember, the cross product is the one where you start with I, J, K, and you have your vector 1, and then your second vector, and you have to do the repeat the first column and the second column, and then you do the determinant. So you do cross, 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 minus cross, 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 and that gives you this third vector. In this case, it's going to be the binormal when you do it with these two vectors. And the order does matter, so your tangent vector has to be the second one and your normal vector has to be the third one, or else you'll get the wrong direction. But when you do that, you get this nice configuration here. Actually, this little organization goes in a couple different ways. So there is one sort of tricky way to organize these. If you want to write this little triangle, the T goes on the top. That's how I remember it. T goes on the top, and you have B and N in alphabetical order on the bottom, and this is arranged clockwise. So here's the triangle that arranges the tangent, the normal, and the binormal. So here's the way that you read this. Let me just make sure that I'm doing this right. Yeah, so if I read it this way, tangent and then normal and then binormal, you can go tangent cross normal will give you the binormal. And you can read this sort of starting in any place. You could also go normal around these arrows, normal cross binormal, normal cross binormal gives you the tangent. You could start here, binormal cross tangent would give you the normal vector. And then we would be back at the beginning. But this is all a cycle, and each one cross the other one in this particular order gives you the next vector in line. Now, oh shoot, I guess this isn't going to show up. Dang it. I thought this was going to show up and show you a cool little animation, but I guess not. There was like a little animation of what these things look like, but I suppose I can't show it to you. But all you really need to know is that these three vectors fit together like this. I think if you look up on Wikipedia, I want to say you look up Frenet structure. On Wikipedia, it shows this cool animation of a tangent, a normal, and a binormal sort of traveling around a function. You see how they all interact with each other. So that's what I was going to try to show you there, but it is not showing up. So if you want to just look for that on Wikipedia, you can do that. And now that we've talked about the tangent, the normal, and the binormal vectors, you're pretty much ready to do all the exercises on here. I think the last two, numbers 15 and 16, are just asking you to find tangent, normal, and binormal. So I'm giving you, this first one is just a 2-component vector, and the second one is a 3-component vector, and you'll start by finding the tangent, then normalize it, which might make it a little bit uglier, but that's okay. It's just how we like to work with it anyway. Basically the same process finds you the normal, and then to find the binormal, you're going to cross those two together. So use the cross product to find the binormal vector, and you'll specifically plug in t equals 0 when you're done on those. In the end of today's notes, I did give you solutions to the exercises, so you can check what you're doing as you go, and if you have any questions, we can talk about those in our office hours this week. So be sure to check your email to see when those are, because the schedule was tentative office hours, so make sure that you check the schedule and figure out exactly when they are for this week. And then email me if you have any questions.